All right, let's get rolling. I brought some toys today, so we're going to see how smart you guys really are. I'll put you to the test. All right, so today we're talking impact. We talked momentum. Is it Thursday already? Yeah, Thursday or Tuesday. Today we're talking impact. We're going to be looking at what we call collinear impact. So everything kind of happening in one line. We're hitting these two balls in a line through the center of mass. Next time we get together, we'll look at running into things at an angle. So what we call oblique impact. So for today, everything is one line. All right. So we kind of started this story last time we were together. Imagine if I've got A and B crashing into one another. We talked about the fact that conservation of momentum would occur here because the only forces I have would be some internal force between A and B. Those would be equal and opposite. So we set up conservation of momentum. And how do we do this? We said, I'm going to just pick the x direction today. Everything we're doing is in one line. So if I looked at this vector equation only in the x direction, my direction of impact here, I would say the mass of A, the velocity of A before impact, plus the mass of B, the velocity of B before impact, is equal to no impulse because momentum is conserved. I'd have a positive and a negative piece, so they would cancel out. The mass of A, velocity of A after impact, plus the mass of B, velocity of B after impact. So we started with this. This is where we ended, actually. And then we did an example problem where I said, hey, I got these two trains coming at different directions. I've got train A, we've got train B, and they smash together. Let's figure out how fast they're going at the end, and let's figure out the energy loss. And we cranked through that, and we did that. But if you think about what we did, we swept something under the rug. I look at this one equation that I have, and maybe I know what's happening at state 1 over here before impact. I can track how fast these guys are going. But then after impact, I've still got two unknowns. I don't know the speed of either ball or either particle or either whatever. You know, last time we got together, we said, hey, these two trains that smashed together, they became entangled. And because they were entangled, their velocity was shared. So the velocity of one was equal to the velocity of the other. In general, that's not going to happen, right? You see two things smash together all the time, and two things come out. They might not look the same, but again, they don't always get entangled. So we get to this part where last time we got together, conservation of momentum, awesome, but it's only one equation. I got two unknowns. We need more info. That's what today's talk is about. Give me more information so we can start solving for these velocities post-impact. Okay. Nothing's terribly important here. The notation I'll use, minus is pre-impact, plus is post-impact. The rest of this story I've already told. All right. To do this, there's a lot of pictures here, a lot of integrals, a lot of whatever. Just listen to the story. Figure out what's happening. So what we're doing is rigid bodies. We got like particle A, particle B. But when we're thinking about impact, we really need to like picture some flexibility happening. So as these two balls come together, they're going to hit each other, right? And during that hitting, just for like a tiny little split second in time, you can imagine they're going to deform. They're going to get squished together. and then they're going to kind of take their normal shape and fly apart. So imagine you took like, two playground balls and you threw them together. This is kind of the picture we'd be seeing. So as they're coming together, this one is going to catch up to its buddy. When they meet, we call this the deformation impulse. There's going to be some part in time where they're squooshing together. It might only be for a couple milliseconds, depending on how much deformation you can handle in these balls. But there's going to be a deformation impulse. They're going to squeeze down. And then there's going to be a point in time, I'll later call this VC, this velocity at the central time of this impact where they're squeezed together and they are traveling together. So they're almost like the two balls have become one, and now they're about to come apart again. So we're flying, we squeeze together, momentarily we're stuck together, and then we start expanding back out. That expanding back out, we call the restitution phase. That's this guy. Hey, we're restoring to our normal shape. So these balls are coming back into ball shape, and then after that, they're flying away. Okay. This is kind of the whole story of what's happening. Come together, squeeze down. For a moment in time, you're traveling together, and then you're expanding back out. So these impulses, the deformation impulse and the restitution impulse, those are going to help us decide, hey, what's happening during this collision? Am I losing energy during this collision? How fast are we going after this collision? It's all going to be kind of based on these two integrals that we're never going to calculate. Okay? So whenever something gets squeezed down and then takes its shape again, there's going to be some amount of energy loss, right? You can think of collisions between maybe like two balls of silly putty. Well, they're going to squeeze in, they're going to really deform. Hey, well, what's happening during that deformation? All that material is kind of moving around itself, squeezing in. You're losing energy to heat. But some of that energy is going to be stored elastically, right? It's like these balls are like springs. They're going to squeeze together. They're going to hold that potential, and they're going to give it back. So you're going to lose some energy. How much energy? That's material dependent. Depends on what two things are crashing together. And that's where we're going to come up with this idea, coefficient of restitution. So the coefficient of restitution, we're going to give the letter E. And this coefficient is going to be the ratio of our restitution impulse over our deformation impulse. Okay? So by looking at this ratio, because we're losing some amount of energy during that impact, the restitution impulse, the force integrated over some time, is going to have to be less of an impulse than our deformation impulse. Like we can't get more impulse out than we initially put in, especially if we're losing some energy. So in this case, when we look at these, the integral of our deformation impulse, is going to be greater than or equal to our restitution. So if this is the case, when I start looking at what we've got here, this is going to tell me that my coefficient of restitution, the biggest it can be is when these guys are equal, 1. The smallest it can be is if I squeeze these guys together with my deformation impulse and they don't restore at all. R is 0. There's no rebounding between them. So my coefficient of restitution is bounded between 0 and 1, depending on how much energy is given back. If we get 1, we call this perfectly elastic. I missed an R in there. So no energy lost. We'd love to be there. In reality, you can't be to 1, but you can be 0.9, 0.98, some pretty high numbers. 0, We call this plastic. And it's perfectly plastic again. I'm just going to, don't ever embroider that. Perfectly plastic. Our two things are squeezed and then no restitution, no pushing back. This is our trains that became entangled, right? Like they just crashed together and they were stuck like that. Everything in between, you've got some amount of elasticity. It's giving some of that energy back, but not all. And that's where the real world typically lives, right? Somewhere between 0 and 1. All right. So if this is my definition of coefficient of restitution, and you think, I've got these two balls smashing into one another, do you really want me to go in there for this deformation impulse and look at, hey, this might be our normal force between those two balls, and do you want me to integrate that over a tiny little time window? And then do you want me to look at the restitution between these two balls and integrate that over a tiny little time window? It's like, no, you can't do that. We need a better way to define this, a way that's a little easier for us to use. Our coefficient of restitution ends up looking like this. VB after impact minus the velocity of A after impact is the velocity of A before impact minus the velocity of B before impact. That varies a little from the notes. The notes use 1 and 2 instead of plus and minus. I like to stick with plus and minus, so sorry about that. This is like a form we can handle now. I will go about trying to show you that this is what actually comes out of that. But for now, just bear with me. Think about, if I've got this equation for coefficient of restitution, this gives me information about the velocity before, the velocities after, and this E, which is going to be a material property, or a property of the two things impacting one another. So this sometimes you can find experimentally. This sometimes you're going to be given. But this equation, assuming you know E, is adding like one more piece of information to our toolkit. So from coefficient of restitution, I've got this. From conserving momentum, we've got MA VA minus plus MB VB minus plus mass times or velocity after the impact. So remember what we talked about, like, hey, this is what I want to use this equation, but I don't know information enough about A and B. Well, if we're given information about the coefficient of restitution, how elastic this impact is, I've got another way to tie those velocities together. So now we're at that two equations, two unknowns part. If you don't know the coefficient of restitution and you don't know both the velocities exiting, well, now you've got two equations, three unknowns. It's not going to do you any good. But in the world where you might know this value, whether experimentally or from a table or some other source. Okay. How the heck do we get this equation from, remember it looked like this, the integral of our restitution impulse over the integral of our deformation impulse. We're going to use our impact momentum to figure this out, just to kind of tell the story here. So, again, if you guys are, what equation do I need to know and how to apply it? This one and this one. You can just sit back and put your feet up. How do we get there? If we think about what's happening to these particles throughout their impact. So if we start with the deformation case first, this deformation phase. I got these two balls, A and B, and they're moving. Who knows? I'm going to look for the deformation phase when they're apart until they're coupled together, moving at a shared velocity vc. That's kind of the first half of our story. So to do that, we can look at impulse momentum for the individual particles. We could look at particle A and particle B. Right? So for A, I would have the mass of A times the velocity of A before the impact. This impulse, deformation impulse, it's going to be pushing back on A and pushing to the right on B, right, as these things get squeezed together. So really, remember, this is a vector equation. So I've essentially picked the positive x direction to the right. So I've got mass times velocity. Now I've got my deformation impulse. But it's pointing to the left. So minus the integral of my deformation is equal to the mass of A. And how fast is A moving? At this coupled speed, vc. Same thing for B. mb, velocity of B before the impact. Now my deformation impulse is pushing to the right on B in the positive direction, so plus. And that's going to be equal to mb vc. All right. I got two equations. They share vc. So we want to solve one of these equations for vc, plug it in to eliminate that variable. So eliminate vc. All right, let's solve A for vc. So I'm going to divide everything by the mass of A. I'll have v of c, this is my A equation, is equal to VA minus, because my MA's will cancel, minus the integral of my deformation impulse over the mass of A. Take this and plug it back in. Let me do this real quick too. I'll do the same thing for B. Just makes my life a little easier. VC is VB minus plus the integral of d dt over mb this time, as I divide through by mb. Okay, so these guys are equal. I can just set these two equations equal to each other. Okay, so if I set the two equations equal, I got what's happening before the impact, VA minus and VB minus, plus some information about my deformation impulse. I can pull out what that deformation impulse looks like. So if I solve this for my deformation, move this guy, I guess, to the other side. And I would have VA before the impact minus VB, moving this one over, before the impact is equal to my deformation over MB minus a minus plus my deformation impulse over MA. So this is 1 over MB plus 1 over MA times my deformation. All right. So what the heck did that get me? Messy, but I've got my deformation impulse, which was the denominator in my coefficient of restitution equation. If I sneak this over, we figured out this guy. Hey, the denominator, the deformation impulse, looks an awful lot like the denominator in the way we want to use it. VA minus VB minus. So the only difference is we got some coefficient here. Some little ratio of their masses coming along. Not a problem. If you did this exact same rigmarole again, but for the restitution phase. So the restitution phase, we're going from this coupled system, going at VC, to A and B traveling on their own. The story we're going to tell is exactly the same as what we just did, so I don't want to do that again. Here is, in the notes, particle A. I've got, for particle momentum, I've got the mass of A times its velocity minus the restitution impulse is equal to its velocity after the impact. Particle B, same thing. What we can do is we can rearrange these equations and solve for that restitution impulse. Hey, and that's what we get. We get the restitution impulse is equal to what's happening after that impact. VB plus minus VA plus. And luckily that same coefficient out front. So again, we just do exactly what we did one more time for the restitution impulse, except now we're starting together and ending apart as opposed to starting apart and ending together. And if you go about that, you will get E is equal to, we could put this little coefficient out front, 1 over MA plus 1 over MB times my restitution impulse, 1 over MA plus 1 over MB, my deformation impulse. And what we'll see is we get exactly what I had promised you earlier. The velocity of ball B before impact minus the velocity of ball A, after impact, plus sign, equal to, switch the coefficients around, A before minus B before. And that's the way we're going to use this to help us out and solve these problems. Okay. How do I make sense of what we just did here? How do we put this to use? So picture yourself playing a game where you're impacting things together. Like pool. Pool's a little funny because the balls are rotating and spinning too. But you've probably played shuffleboard, or we're in Wisconsin, maybe you've seen curling even, where you're pushing something, it's hitting something else, and it's transferring that momentum, right? So you picture in your head, what happens as I'm playing shuffleboard and I push this puck, it impacts another puck. Well, what do I think is going to happen? If I hit it straight on, the one puck that you pushed with almost seems to kind of like die, and the other puck shoots off at that about same velocity, right? That's kind of what our eyeball imagines for these problems. So if I was playing shuffleboard, I would have velocity of A coming into impact B, which is at rest, right? And then after that, how fast is A going? How fast is B going? Well, those are kind of the questions we want to be able to solve with this. So when we do that, we'll use our two tools we have. Conservation of momentum for a system of particles, because there's no external forces acting on this, and now coefficient of restitution. So from momentum, I'll pick the x direction positive, and that's what I'm going to look at. So momentum will tell me, let's assume these all have the same mass. So I've got m, if I'm playing shuffleboard, my velocity of A before impact, m, my velocity of B before impact, stopped, so we'll say 0. That goes to mass times the velocity of A after plus mass times the velocity of B after. All right, this is where we were last time we got together. I don't know. 2 unknowns, right? Tell me more info. Coefficient of restitution. This is our next equation. This is the velocity of B after impact minus the velocity of A after impact over the velocity of A before minus the velocity of B before, which B we said was sitting still. Maybe we know the coefficient of restitution for these shuffleboard pucks or pool balls or whatever we have. So if that's the case, I've got 2 unknowns and 2 equations now. We can solve what's happening here. So if we do that, let's get rid of one of these guys first to see what's going on. All right, so I'm going to rearrange this and solve for velocity of A to get rid of that one, at A after impact. So if I did that, I would multiply the denominator across, and I would have the velocity of A after impact is equal to the velocity of B after impact minus E times the velocity of A before the impact. Just rearranging this equation to solve for one of these guys to get rid of them. This we can now plug in. So if we plug in, I've got my mass times my velocity of A before the impact plus 0. There's the equal sign here. I just kind of skipped it and put an arrow instead. Sorry. Is equal to mass times substituting in for A after the impact. Velocity of B after minus E times the velocity of A before. Plus M velocity of B after. Okay. Everything's got a mass term. We're assuming these are all the same pool ball, all the same shuffleboard, all the same curling puck, whatever it may be. Let's put like terms together. So here I'm left with VA before impact, moving this one over, 1 plus coefficient of restitution is equal to, I got a pair of VBs. So this is telling me for B, after impact, it's equal to 1 plus E over 2 times the velocity of the ball coming in. If I also wanted to figure out the velocity of A afterwards, hey, not a problem. I've already solved for velocity of B plus. I could just go back and solve for now the velocity of A after the impact. This is VA minus times 1 minus 1 plus E over 2. All I did was solve the other side of the equation. So this is telling me what's happening to either ball after the impact. Let's see if this matches what our eye would think. So when you're playing pool, these balls have a crisp impact, right? They're both pretty hard. There's not a lot of elasticity. They're not deforming a bunch. So that impact is going to be pretty darn close to 1. E is 0.9-ish, right? So if you think about what's happening to ball B as it's getting impacted by ball A is coming in. This coefficient, 1 plus something that's close to 1, divided by 2, this is about 1. If E is 0, or sorry, if E is 1, if E is approximately 1, then the velocity of B after the impact is about the velocity of A before the impact. Oh, hey. When they hit, this one's going 2 miles an hour, then the one leaving is going about 2 miles an hour. A little bit slower, because E can never be greater than 1. So it can't be going faster than the guy that hit it, if they're the same mass. And then for A, the ball that's doing the impacting, how fast is it going? If I have E is about 1, so here E is about 1, so we got 2 over 2, that's 1, 1 minus 1, 0. So this is about 0. So if you think about last time you played shuffleboard, you pushed that disc real fast and it hit your buddies and you laughed and his flew into the gutter and then yours just stayed there, almost stopped immediately, right? That's kind of what you're seeing here. The one that got hit from a standstill gets launched off. The one that does the hitting, hey, almost comes to a dead stop. And it comes to a dead stop if E is equal to 1. But if E is greater than, or sorry, less than 1, it's going to have a little bit of velocity. It's going to continue to move. And maybe that's the important part to look at is that, hey, it is less than 1. So I've got 1 plus something less than 1 over 2. This is less than 1. 1 minus something. This is going to be a positive number, right? 1 minus something smaller than 1. Positive number. So if this guy was moving to the right, then A, after the impact, also still moving to the right. Because this we know has to be positive. That kind of fits our intuition, I think. All right. This is the page of the notes that you're going to refer back to, right? Our two equations that we're going to use for these collinear impact problems. Conservation of momentum, coefficient of restitution. If you remember that, you remember how to apply these properly, we're going to be in good shape. The word of warning is that these are only right now for collinear impact, two things kind of moving exactly on one line. Next time we get together, we'll talk about, well, what happens if one is coming from one angle and the other angle, or they hit slightly off center? Then we've got another problem to deal with, but we'll deal with that when we get there. All right. Time to blow your minds. I've got this little impact toy. There is a ramp, and I have balls of various weights here. What I'm going to do is I'm going to put one ball down here. I'm going to roll a big one down the ramp, and it's going to push its buddy out of the way. It's going to impact at the bottom and impart its velocity, and it's going to travel up the hill. All right? So what does this take into that we've known? I know from work energy, if I start this ball here, how fast it's going at the bottom. I know from impact, when these two guys hit, how fast this one's going to go, if we know the coefficient of restitution, right? And then I know from work energy, again, now that I have some velocity imparted to the little ball, how far up the hill it's going to go. Right? Energy, kinetic, half mv squared. Opposite side of that equation, potential energy, mgh. How high up the ramp have I gone? So, nothing terribly fancy. Two things that we already know put together into one demo. Now, how smart are you? That's the idea. I've got this ball, my big one, 50 grams. I've got my medium one, 28 grams. I've got this little green one, 4 grams. And I got this tiny little ping pong ball, half a gram. When I impact these 3 different balls with the big one, what do you expect to happen? You expect the big one hitting the medium ball goes like halfway up my ramp before it gets to this notch. If this guy weighs 1/7 of the last one, what would you expect? It's going to go higher or lower or the same? Yeah, it's a little. It's going to go higher, right? And part of the story that we're not talking about is, well, it's the coefficient of restitution on these balls. Are you trying to trick me? But they're all pretty bouncy. Like they're all, none of these are like trick dead ball. But if they were, that would affect it. So this one goes kind of halfway up. The green one, 4 grams, goes almost to these stanchions. I'm sorry, I know it's this tiny, guys. But it goes almost to the stanchions, so like twice as high up. The white ball, which is 9 times lighter than the green ball, what would you expect? My ramp ends here, right? This thing's 9 times lighter than this. This one was 7 times higher. So I understand that lighter, it went further, right? So you put that one in there, and you roll down. Oh, it doesn't really go any higher. It goes a little higher, but marginally higher, right? So what the heck's going on? This one is 10 times lighter than this one, but yet when I hit them, it doesn't go that far. That's question 1. Now, this green one, when I dropped it down, goes about to these vertical pieces. What would happen if I added these 2 balls together? I put the steel one and then the green one after it. And what does your brain tell you is going to happen? So I guess my brain could tell me, hey, that middle ball, all it's doing is acting like a solid. It's just going to transfer that force. That green one's going to go the same height. Plus a diameter, right? My brain could tell me, well, when you hit that, both those balls are going to roll. So both those balls must have stolen some momentum. And therefore, the steel ball is rolling and the green ball is rolling. I'd expect them to both go less high. And then you think, I'm going to drop this ball down. They're going to impact each other. And the green ball is going to go further than it did before, like twice as far. And you think, well, why'd that happen? You say magic, right? So, show of hands, same height-ish. Who thinks that? First option. Come on, get those hands up. Don't be scared. Who thinks it's going to go less high because the momentum is going to be stolen? About the same number. Who thinks magic? Yeah, magic. Yeah. I wouldn't show you if it wasn't magical, right? All right, prepare to be amazed. Way higher. Oh, no. I got this white ball. I'll put the white ball in the mix. Remember, the white ball went to here before. It goes all the way to the top. I don't know what's going on, guys. Okay, now, new problem. What if I swap the order of these balls? I take green and the steel one and I give them the old switcheroo. What's going to happen? Same? Am I going to blast the white one? Is it going to go further? Nothing's going to change? Who thinks it's going to change? What's going to happen? Lower? Well, I can't go any higher. Ran off. Who's expecting the same result? One guy, one brave guy. Okay. I'm here to blow your minds today, dude. It's not going to be the same result. It didn't go very high again. So the order of how heavy these balls were mattered. And putting more balls in went higher. What the? Math time. I should have just wrote my other notes more carefully because I could have stole a lot of what we did. But I didn't, and now I can't. So, quick redo. We've got impact. Now we got a big and a little smashing into each other. Tell me the story of what is happening here. So, momentum. Again, I'm just looking in the one direction now. So I've got the mass of A, my velocity of A before, plus the mass of B, velocity of B before. We're not going to worry about that one. Equal to the mass of A, the velocity of A after, plus the mass of B, velocity of B after. All right. Now we're on to something. This is what we're interested in. That velocity is proportional, or the square of that velocity is proportional to the height. You could do that from work energy. So let's quick take a trip down the work energy world. We'll just look at, we'll call this after the impact, right? So I got VB after the impact. These two guys have just hit each other. And now it's going to try to drive up this slope. I've got half mb, velocity of B, after the impact, squared. It's not a plus squared. My datum's on the bottom. Datum is equal to how high it goes, right? So this would be like our T2. But at the top of how high it goes, it's paused, so it has no velocity. But it's gained potential. It's gone up some height h. So MBGH. We can rearrange. My MBs on both sides will cancel. My h is equal to VB plus squared over 2G. So, all we've done, short trip down memory lane to remember, what was work energy telling us? Work energy was telling us, if I know the velocity, I can relate that to how high it's going to go. Changing kinetic for potential energy. That's all we did. But now for us, if we know how fast it's going, we'll get an idea of how high it's going. That's our eyeball to gauge. We don't really need that to solve today's problem. It's just to tie everything together. But I've also got coefficient of restitution. So here, our coefficient of restitution, velocity of B after impact minus the velocity of A, after impact over velocity of A before minus the velocity of B before, which we said was 0. All right, I want the velocity of B after impact, so I'm going to solve this for the velocity of A after impact so I can eliminate that variable. Velocity of A after is the velocity of B after minus the velocity of A before times our coefficient of restitution. Hey, we just did that. This, and plug it into my momentum equation. All right, plugging it into our momentum. ma, velocity of A before, is equal to ma times what we just solved for, my velocity of A after. VB plus, and I'll just do this right away, minus ma E times VA minus plus MB VB plus. All right, I'm interested in my velocity afterwards. That's what I'm going to solve for. Velocity of B after the impact is equal to 1 plus my coefficient of restitution, the mass of A, the velocity of A before impact, over the mass of A plus the mass of B. Whoa. Well, what is that going to tell us? Not a whole lot unless we look a little deeper. So if we look a little deeper here, I think this is how fast my ball B is leaving after it's impacted by ball A. In this case, I have B being little and A being big. So let's assume the mass of A is much, much bigger than the mass of B. If that's the case, take a look at this coefficient. The mass of A divided by the mass of A plus the mass of B. So this guy would be mass of A over mass of A plus mass of B. If this was true, that'd be about 1, right? In this case, for the balls that I showed you, 10 to 1, maybe we're looking at like 0.9. And then our buddy from before, coefficient of restitution. If E was about 1, I get 1 plus 1, I get a 2. This guy could be 2. So we just came up with the 2 times velocity rule. This is telling me that the velocity of the thing I'm impacting can be at most less than or equal to 2 times the velocity of the thing it's crashing into. So it can be 2 exactly if, well, it can never be 2 exactly, right, because this is never going to go to 1. But it could be about 2 if I had a perfectly elastic collision and A was way, 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 way bigger than B. But the velocity of B going out is faster. But it's limited. It can only go 2 times faster. So what was the trick I played on you guys, right? When I looked at this equation, actually, let's talk about the first trick I played on you, where I looked at a green ball and the white ball. The green ball was 10 times lighter or 10 times heavier about than the white ball. But when I impacted them as like a single, they went to about the same height. Not that different. And that's because this ratio of masses isn't really that different. So if I look at what I had 50 plus, this was either like 4 grams or a half a gram. Either way, it's a number that's still pretty close to 1. So those 2 balls, even though one was 10 times lighter, you can't get any better than 1, so you're going to get kind of diminishing returns. But the bigger ball that I hit was 30 grams. Now it's like 2/3 of that overall weight. That ratio was way less. Okay? But how did I make that one go so far? If I went like this, and then to like this, and then to like this, and then to like this, right? I stacked up these impacts. And when these impacts, you could think of one happening very shortly after the next, very shortly later, another one, then another one, then another one. If you think about them sequentially, I'm going ding, 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 ding. Pew. What I'm doing is I'm pushing this 2 times velocity rule over and over and over and over again to where now I'm launching that last ball faster than I could have by just hitting it with a big ball. Okay, that is all.